Hello guys, welcome to homework number 31 and 32. I'll go ahead now and share the problems for this homework and go through it with you guys immediately. So I believe you guys can see this. The first problem is focus on concept question 08. It says the nucleus 244 and 94 of, I think that's plutonium, is radioactive and emits an alpha particle. Into which nucleus does it decay? So that's the question. So when you emit an alpha particle, which is a helium nucleus, so you're going to take 4 from the mass number, and then you're going to take 2 from the electrons right here. So you're going to have 240, 92 left to make the alpha particle. So the answer of what's left of the nucleus, which it decays into after emitting an alpha particle, will be 240 for mass and 92 for number of electrons or protons right here. So focus on concept question 14 says, after 2 days, only 1/4 of a radioactive sample remains. What is the half-life of the nuclei? So there are 2 ways to approach this problem. The first approach is to use the relationship for the number of atoms or number of the radioactive particle or nuclei left compared to the initial n0 of what's left. So n at any time equals n0 over 2 to the power n, where n is the number of half-lives. So this is the simple way. We're going to see a similar problem, and I'm going to solve this similar problem in a different way. And if you use that same way for this problem, you get the same answer. If you use the same way for that problem, you get the same answer. So now it started from n0. Now you're going to go to n0 divided by 4. So n0 over n over 4 equals n0 over 2 to the power n. How many n's will decay from n0 to n0 over 4? Don't forget that this 2 is part of the formula, so don't let this 2 denominator here confuse you. So it's just this n that goes to 1/4, 1/4 of the radioactive sample. So n becomes 2. So n0 over 4 is n0 over 2. Then when you square that, it's just 2 squared. So it's just going to be 2 right here. So n is 2 to make this work. Because n here, we're going to put 1, 1 and 1/4, if you like. So this is 1, and that is 1/4 of whatever it was. So we just put 1 there, if you like. And then you're going to get your n here to be 2. So 2 is 2 days. So that's 2 half-lives. It took 2 days, according to the problem, after 2 days. So 2 days corresponds to decay to 1/4, and that n equals 2 half-lives. So what is 1 half-life? 1 half-life is 1 day. So this is the simple way to get the correct answer to this problem, to be just 1 day. Okay, the next problem, focus on concept question 17, says each of the following items is about 5,000 years old: a tooth, a rock, a stone arrowhead, a forecap, a clay pot, and a deerskin moccasin. Which one or more of these items can be dated using carbon-14? So this is used for living organisms or something related to living cells. So the rock cannot be there, the clay pot cannot be there, the stone arrowhead cannot be there. So it's just the tooth, the forecap, and the deerskin moccasin. That becomes the answer to that. Okay. Sorry about that. Let me silence my phone right now. Okay. So the next one says chapter 31, problem 05, says in a real or imaginary nucleus of X14768, how many protons are in the nucleus? So number of protons in the nucleus is Z, which is 68 down here, number of electrons, if you like, for a neutral nucleus. How many neutrons are in the nucleus? So for neutrons, you have to subtract the mass number of protons from the mass number, because the mass number is total of protons and neutrons. So 147 minus 68 will give us the number of neutrons. And then how many electrons? Electrons for a neutral nucleus is equal to the number of protons, which is 68 still. So that's how you do this problem. Okay, the next problem is for lead 20682, atomic mass 205.97440 atomic mass unit, obtain the mass defect in atomic mass units and the binding energy in mega electron volts and the binding energy per nucleon in the mega electron volts. So how do we get the mass defect? So we calculate the number of neutrons bit by bit. So 206 minus 82 will give us the number of neutrons, 124. Then how can we get the mass defect? So what we're going to do is we're going to take 82 for free hydrogen atoms like the protons plus electrons. The electrons don't usually count much, but is 1.007825 atomic mass unit for number of hydrogen atoms times 82. That's the total number of protons. Then total number of neutrons, free neutrons, is 124, we just calculated, times the atomic mass unit for neutrons. So this should be in the tables in your textbook, 1.008665 atomic mass unit. So we sum those up, and then we subtract from them the atomic mass of these without considering the constituent. So we see there is a difference. So this is what constitutes the binding energy when there's a difference. So this is the mass defect, okay, for the A part. So the B part, for the binding energy, we just convert that mass defect to electron volt. 931.5 mega electron volt is 1 atomic mass unit, and then we get the answer in mega electron volt. And then the binding energy per nucleon is binding energy divided by the total number of nucleons. So that's going to be this answer divided by the nucleons is protons and neutrons. So it's going to be this divided by one, what is it right here for the nucleons? 206. So we're going to have 206. So that's 1620 divided by 206 becomes the final answer right there. Okay, the next one is chapter 31, problem 32. And it says that in 110 days, the number of radioactive nuclei decreases to 1/8. What is the half-life in days of the material? So this is the same problem I told you could be done like the first problem, but this is the second method. So you're going to combine two formulas, n equals n naught exponential minus lambda t, and lambda is 0.693 over half-life. So from here, we're going to put lambda in this formula and solve for half-life. So n over n naught, you're going to solve for half-life to be 0.693 over ln n over n naught times t, the total number of days, okay? So n over n naught, n is say 1/8, n naught is 1, so it becomes 1/8 divided by 1, which is 1/8, ln 1/8, ln 1 over 8 over this. So when you solve this, you're going to get a negative number times a negative number, gets a positive number. When you multiply, you get 37 days. Or you can do the n naught, n equals n naught over 2 to the power n, and then find n. So you're going to get n to be like 3 or something. Then you divide 110 by that, and you're going to get 37 days also. So whichever method you solve the problem to get your half-life, you're going to get the same answer in this case. Next, chapter 31, problem 34 says an isotope has a half-life of 23.89 days. What is its decay constant in units of per second? So half-life is 0.693 over lambda. So lambda is the decay constant, 0.693 over half-life. So it's 0.693 divided by 23.89 days, and then you convert that to seconds. Is that okay? And you get that there in seconds. Okay. So 1 day is 10 to the 4 seconds approximately. So that's how you convert this. And you can do it bits by converting to from day to hours, hours to minutes, minutes to seconds, as you like. You're going to get the same answer basically. But it's just a direct conversion constant here. 1 day is this 8.64 times 10 to the 4 seconds. And then you multiply by your answer in days, and then you get the answer right here. So next one is chapter 31, problem 38. It says a certain radioisotope has a half-life of 9.20 days. What percentage of an initial sample of this isotope remains after 35 days? So n over n naught equals exponential this. So you are given the half-life and you are given the number of days t. So t over half-life is 35 over 9.2 days. And then you are asked how much is left. So n over n naught is the fraction, the percentage of the initial. And n naught is the initial. This is what is left. The percentage is n over n naught. That's what we're looking for, 0.0716. So we'll just convert that to percentage. It gives us 7.16% for this particular numbers in this problem. So your numbers might be different. Just watch out for that and just follow the same process here. You should get the same answer. Then the next one is chapter 31, problem 39. And it says, the number of radioactive nuclei present at the start of an experiment is 2.07 times 10 to the 15. The number present 20 days later is this. What is the half-life in days of the nuclei? So we just solve from here, n equals n naught exponential minus lambda t. We solve for lambda, the decay constant. We get the decay constant to be this, and then our half-life is 0.693 over decay constant. So just putting formulas here and there, and working carefully with your ln, the natural logarithm. You can find that in your calculator, ln, you just click it, whatever value you get here, put it, it will give you the value there. Sometimes it's negative, and then you multiply by the negative here, it makes it positive. Okay. Next one is focus on concept question 08, and it says the binding energy per nucleon has a maximum value of about 8.7 mega electron volt per nucleon for a nucleus with a nuclear number of about A equals 60. So for nuclear numbers greater or smaller than 60, the binding energy is less than this maximum value. So consider the following two nuclei, one less than 60 as A, one equal to 60 as A. So which of this reaction is potentially energy producing reaction? So energy producing reaction means when they combine together, they don't have enough energy to produce the product. So they have to produce energy from the combination to add to their combined masses in atomic mass unit to produce that result. So since anything less than 60 cannot have this maximum value, so when I sum this together for reaction 1, I cannot have 60. I cannot have the maximum value because these initial ones are less than 60. So these ones need to produce energy to add to their initial values to produce this 60. So reaction 1 is the answer, is the one that will potentially be energy producing. So these ones already have the maximum value. So when they combine together, they can just give the 120 for sure. Okay. But anything less than that or more than that will need a potentially energy producing reaction. Okay. Focus on concept question 10. The drawings show 4 possibilities for hadrons in the quark theory. In each of the possibilities, the symbols for the quarks are shown together with the corresponding electric charges. Note that E stands for the magnitude of the charge of the electron. Which one shows the quark structure for an antiproton? So a proton has 2 up quarks and 1 down quark. So an antiproton will just have anti-quarks, 1 anti-up, 1 anti-up, or 1 anti-down. So the correct answer here is just D. So just change all the up, up. So this is a proton, up, down. So change this proton by swapping all these anti-up, anti-down, and then changing the signs of the charge. And that will give us this guy here. So B is a proton, D is an antiproton. So the correct answer for antiproton is D. Focus on concept question 11. Which one of the following statements is not accepted as a part of the current picture of the universe? The correct answer is A. So let's look at the rest. The universe is expanding, correct. Early in the history of the universe, there was only one fundamental force, correct. The weak electromagnetic radiation in the microwave region of the spectrum that bathes the Earth provides evidence of the Big Bang theory, correct. The universe began with a cataclysmic event known as the Big Bang, correct. So why is A wrong? Hubble's law indicates that a galaxy located at a distance d from the Earth is moving away from the Earth at a speed that is inversely proportional to d. No, not inversely proportional. Is that okay? That's not what Hubble's law says. So this is wrong. Okay. Okay. Chapter 32, problem 31 says 2 deuterium atoms H21 react to produce tritium H31 and hydrogen 1,1 hydrogen according to this reaction. The atomic masses of deuterium, tritium, and hydrogen are given. What is the energy released by this deuterium-deuterium reaction? So 2 deuterium combine to form a tritium and the normal hydrogen that we know, apart from these isotopes. So the reaction is 2 of these guys combined. So we put the 2 hydrogen combined in atomic mass unit. This is the tritium mass, plus you can get all these values from your tables in your textbook, hydrogen mass. So we're gonna get the what is it called? The mass difference first. So these two give this, these two give that. The mass difference is this minus that, 0.004329 atomic mass unit. So we'll convert that to electron volts. The mass difference is gonna give us the energy released for this reaction, multiplied by 931.5 over 1 atomic mass unit. And we go to the next problem. Focus on concept question 11. Oh no, that's actually the last problem. We've done this before, sorry. So this is actually the last problem, and then thank you guys. I'll see you guys next semester maybe. This is the last homework, and I wish you guys good luck in your exams, and I hope you enjoy this class. Have a good one. And say big thank you to Tonya. Tonya is the professor of the year. Have a good one, guys. Bye for now.